Last time we talked about sampling, and we said that, let's see, sampling. We said that if we have a continuous time signal that's band limited, so let's say x of t only has frequency components less than some upper bound, the magnitude of f less than some bandwidth. Okay, meaning that the Fourier transform is 0. So what we mean by that is h of f equals 0 for f greater than this bandwidth. Okay, and if that's the case, if that's our assumption on the signal itself, then we can successfully sample, let's say here's our signal, x of t, and we can take samples of it so that what comes out here is a discrete time signal. X of n, and as long as the sample frequency of sampling is greater than twice this bandwidth, then we can recover. Now, last time I put this backwards. We derived why we need this inequality, but I put the 2 on the wrong side of the inequality. So the notes from last time have a mistake. Then we know we can recover. And the way we would recover would be, we would have, on this side here, we kind of need to do it in 2 steps. One is, we need this discrete time signal to be represented in continuous time with delta functions. Okay. I'll represent it with 2 steps here. We'll really be doing it 1 step, but so kind of in between, let's say we just convert it into the continuous time representation. So maybe we have some circuit that produces delta functions based on the discrete time signal. And then we do a low-pass filter with the cutoff frequency being what? Fc equals half of the sampling frequency. Fs over 2. And then what will come out will be our original signal here. X of t. Recovered. Now let's review why this is going to happen. So it's pretty remarkable. We sampled discretely. We threw away everything between the samples, and yet we didn't lose any information. We captured the entire signal. Very useful to understand this, because this is exactly what we've done in every lab that you've worked on involving sound. You've been dealing with discrete time signal. Okay, so let's think about what, well, okay, before we rederive, we'll kind of refresh on why this worked. But first of all, let's imagine that audio signal, the ear can only hear up to a certain frequency. Does anyone know how high your ears can hear? What did you say, 20,000? Yeah. 20 kilohertz? And in fact, a lot of people can't hear above, say, 15 kilohertz very well. So 20 is really capturing the best range that people can hear. So ears above 20 kilohertz. There's a lower end of that range as well, but we'll just assume it's 0. Okay, so so that means that now, just because the ears can't hear above 20 kilohertz doesn't necessarily mean that microphone picks up doesn't have anything above 20 kilohertz. It probably does. Just because your ears can't hear it doesn't mean those pressure waves aren't there and that the microphone didn't pick them up. So does it matter to us? If we sample anyway at our, well, okay, so what sample, so suppose that that 20 kilohertz is the bandwidth at least that we care about. Then a sample frequency associated with that would be above 40 kilohertz we would want to sample at. Now let me point out here, even though, don't care. Okay, so the answer is it does matter. The stuff above 20 kilohertz you have to remove. It will affect in a negative way your samples. Okay, so even though we don't care about it, we can't hear it. If we don't remove it and we go sampling, it's going to turn into an artifact that we can't hear. Okay, here's why. We'll go through the derivation again. So, okay, so if we low pass filter first, at the cutoff frequency equals 20 kilohertz, then sample with sampling frequency Fs greater than 40 kilohertz, then we can recover the sound, the audible part at least. Exactly. So we don't lose anything. Now there's a lot of ideal things going on. I'm assuming we do an ideal low-pass filter here. Nothing's going to really be ideal when we implement it. But anyway, if we could do an ideal low-pass filter to get rid of the inaudible parts above 20 kilohertz, and then we sample, we do some ideal sampling above 40 kilohertz, and then we recover in this ideal way where we make delta functions in low-pass filter, then we get everything back, okay? And in reality, we'll be very close. We'll be able to build an actual implementable low-pass filter and sampling that doesn't lose much, that you can't really tell the difference. Does anyone know what frequency CDs sample at? We mentioned already, 44 kilohertz, 44.1. The exact value is just a technical thing, had to do with the technology of the companies at the time. So that 44, you see, it's just above 40. That's going to allow for some room because our low-pass filters aren't going to be exactly cut off. So they give a little bit of room there, and they sample a little bit of a higher rate. But now we can see why that's designed to be that. So this is called the, this here is the Nyquist criterion. And then this would be that 2 times the bandwidth is the Nyquist rate. All right, so you'll hear that referred to. It's Nyquist doing that. You have to sample it twice the bandwidth. Okay, so let's review why this is true, because now you can derive this just from everything you know about the Fourier transform. So what we said was, we started with some signal where in the frequency domain it was band limited, and I'm drawing it this weird asymmetric shape just because it'll help us keep track of what we've done with the manipulations. Of course, real signals have a conjugate symmetric Fourier transform, but so this would be a complex signal. I'm just drawing it that way for illustration. So let's say here's 0, here's the bandwidth, and here's negative f bandwidth. All right. So this was capital X of f, course, it's really complex valued, and then drawing it as if I can do it in one dimension. Again, it's just a cartoon picture. So now, sampling, we said, can be interpreted as multiplication with a sequence of delta functions. This delta train here, where this is x of t, and the delta train is the sum for k equals negative infinity to infinity of delta of t minus k times the sampling period, Ts. Here, Ts is 1 over the sampling frequency. Okay, so we said that if we do multiplication here, then that's going to give us a bunch of delta functions, each scaled according to the signal itself. I'm just going to draw. These may not correspond, well, I guess horizontally I should at least make them match up. So we're going to get samples where this was the signal itself. Okay, so this is what happens when we do that multiplication. And this is exactly the continuous time representation of our discrete time signal we get after sampling. Okay, so this is a valid way to think about sampling. And now that we have this way of interpreting sampling, then we know by the multiplication rule that in frequency, this goes to a convolution between the original spectrum and the Fourier transform of that function. We derived what the Fourier transform of this delta train is. So this is going to be xf convolved with the Fourier transform of that delta train was 1 was fs, 1 over the sampling period, times the delta train in this domain. Okay, so that means that that type of convolution is very simple, because convolving with a delta function just shifts our signal, centering it the delta function. So this gives zero f bandwidth and then this is the sampling frequency, fs. So this would be fs minus f bandwidth. Okay, and the height also gets affected because we have this this fs out front here. So that means the amplitude, if that was 1, then this goes to fs in height. All right, that's just going to change the scale of our signal. Not that big of a deal right now. Okay. This was what happens if there was no overlap. And to get no overlap, you need this to be greater than this. Right? So if fs minus f bandwidth is greater than f bandwidth, therefore fs is greater than 2 times f bandwidth. So there we see at least it's sufficient. This is a sufficient condition to get no overlap. Yep. Okay. The red is basically saying that after doing this multiplication between the original signal and this, this is the Fourier transform. Maybe I'll put that on there. Yeah. Okay, if, no, yeah? Well, a constant, so convolution is linear, so if you multiply one of your signals by a constant, then the result is that. So if that weren't there, then it would keep the same magnitude. Where does the constant go when you write out the expression? Well, the expression is going to be a sum, but this fs is part of this signal. No, sorry. I mean, like, how do you get it from the the Fourier transform of the delta function train has fs in it. When we derived it, it had the 1 over t, and I'm just replacing that with that. Okay, so, okay, and notice that if we didn't have that, we'd have something like the following. We'd have this thing, but if our sample frequency was too low, that would overlap, right? And what happens with an overlap is these all get added together. Okay, so let me make that. So this is if fs is less than 2 times f bandwidth, then we can get overlap, and the result is that we get a sum here. So we would get something like this, and here it would add up. Okay, so we would get, and what we call this here, people refer to this as aliasing, because we already said what aliasing, we already defined that aliasing in a discrete time signal is when two frequencies look the same. Or can be called by, one signal can be given the label of 2 different frequencies. Okay, and that happens in any discrete time signal. Well, now we see that same, because of that same problem, you've now confused what started as one frequency. You have some frequencies some frequency constants way up at the edges. That now that you've sampled at too low of a rate, you've confused whether they're high frequency signals or whether they're low frequency signals being interpreted in the next copy of your spectrum. Okay. So what that means is you now, because you sampled at too low of a rate, you have some ambiguity at the high frequency edge on whether it was a high frequency or low frequency due to aliasing. Okay, and that's not good, because what's going to happen is you're going to have to make a decision. When you want to turn this back into a continuous time signal, you're going to have to decide how to reconstruct this thing. And the typical way is to do a low-pass filter. Filter out all the high-frequency stuff. And what will happen then, okay, so for reconstruction, remember, reconstruction is going to be a low-pass filter. So you're going to just, so you're going to come up here and apply a low-pass filter like this, and you can put the gain in there to cancel the sample frequency to bring the amplitude back up. Okay, we're going to do a low-pass filter. The height of this low-pass filter will be the sample period, which is 1 over the sample frequency. And the cutoff will be Fs over 2. And you see that you're going to get back your original signal in the top case. Now in the bottom case, if you try to do that, what you're going to do is what you see is that this part, let me highlight it here. This frequency content here and this frequency content here which actually came from a higher frequency. This actually was coming from these frequencies down here. Is what this is. It just got copied out. And this stuff here is actually coming from this copy. So that corresponds to this. But when you apply the low-pass filter, they're getting reconstructed at a different frequency. Okay. And that aliasing effect is an artifact that doesn't sound good or doesn't look good. I'll show you an example of aliasing that you're familiar with. Okay, so you've seen this effect. In a movie, you see a wheel going backwards. Right? All right. This is exactly aliasing. What's happening is the frame rate of the video is not high enough to capture the. What you've done is you've sampled a video in time, right? You've sampled too low of a frequency to make up for the actual frequency of the tire spinning. And so what that means is that your mind interprets the lower frequency version. You know, there's many. This video is consistent with many different rotational frequencies of that tire, and in your mind, you're always interpreting it to be the lowest frequency interpretation, which makes it sometimes look like it's going backwards. I just recorded this the other day. Okay, so we understand aliasing there. So what do we do to avoid aliasing? We have to make a decision. We cannot get all of this frequency. If we're going to do a low sample rate, we can't get frequency content that's bigger than half of our sample rate. Now it's funny, what I'm calling F bandwidth, just so you understand, is actually, if you look at this in the context, if you look at this in the frequency domain of the Fourier transform, F bandwidth is actually half of this entire thing. So one way to think about it is the Nyquist frequency is actually has to just be greater than the entire width, going from the highest positive frequency to the lowest negative frequency. Okay. Now, but since for real signals, the highest positive frequency and the lowest negative frequency are always equal to each other, and that's usually referred to as the bandwidth. Okay, yeah. There can be, actually, it can combat things like noise in your samples. You can get a better, by taking extra samples. It also can make up for maybe not being able to implement an ideal low-pass filter. You can make up for that by taking a higher sample rate. So there are benefits to it, but if you can do the sampling ideally, and if there's no noise in your samples, then there's not going to be a benefit to taking more samples. Okay. So what you have to do is actually filter. It's important that you filter out the frequency content that's going to cause aliasing before you take the samples. Okay. Have to filter it out before you take the samples. Once you've taken the samples, there's no way to then go back and separate out that this little green component actually wasn't part of this frequency content. It's lost. You've confused them now, and you can't separate them anymore. So you have to do the filtering before taking samples. I'll write that here to avoid. In other words, this is usually going to be high frequency. So again, even if you don't care about that high frequency stuff being picked up by your microphone because you can't hear it, you need to filter it out to avoid aliasing. Okay. Now, let me show there are other ways of sampling, less common, but just to show you that we can actually derive different sampling theorems. So suppose for a minute suppose that you have the following frequency content, that x of f equals 0 for all f such that let me assign some bandwidth less than f less than 2 times that bandwidth. Okay, so I've defined some new notion of bandwidth. All right, here I'm not saying that this signal has only low frequency content. I'm saying let's assume it has some middle range of frequency content. It doesn't have low frequency content. It doesn't have really high frequency content. All right. So that means that we've got something that looks like this. There's 0 f bandwidth. There's f 2f bandwidth. We have something like that, and since it's a real signal, it's going to be symmetric over here. Okay, so this is our x of f. Something looking like that. Yes?
I just have a question about the aliasing and everything. If you just get a random signal in, how do you know what the highest frequency is without, like, how do you know what to make your Nyquist frequency if you don't know what the highest frequency is?
Oh.
Like, how would you know the highest frequency?
Well, you would do a Fourier transform, but how are you going to do that in continuous time? In discrete time, you can do it. I mean, it depends sort of on your setting. If this was like this was an optical signal, you can do certain types of spectral analyzers that are the same as doing a Fourier transform, but in continuous time with various sensors. You could come up with some method of trying to sense the frequency content to figure out how high the frequency content is. So there are ways of essentially doing a Fourier transform in continuous time. Okay, but normally you would say, what do I care about in this signal? You have some idea of what you care about even before. You're not just looking at some arbitrary signal. You're saying, oh, I care about a certain frequency range of this signal. And in that case, you don't care about the rest. Filter it out, right? So you apply a filter that removes the range you don't care about. And then it didn't matter if there was a signal there or not. Okay, so in this case, let's say that we do, let's say, okay, so what frequency should we sample out to preserve the signal? Yes? Oh. Oh, wait, shouldn't what be doing? No, because between 0 and FD, I want it to be. Oh, yes, I see what you're saying. Yeah, you're right. It's the exact opposite. So it's because here I'm defining where it's non-zero, and I want to define where it's 0. So this should be F. Good point. Okay. Yep. So this is what we've drawn here. What frequency, if I want to preserve the signal, and I'm going to sample it now, and I'm not going to apply a filter, I want to preserve this whole thing. What sample frequency should I use? Okay, so you could do Fs equals or greater than 4 FBW bandwidth. That's sufficient, right? We know that's going to work by the Nyquist criterion. We didn't even need to know anything about this nonsense about not having anything here. Although we're going to do a trick and use a lower frequency. So Any ideas what we'll do? Yeah?
You know that these two are identical, you don't know.
We're not going to assume it's symmetric. I think by identical you're saying, is this just a shift of that?
Yeah.
And let's not assume that. Even though my picture looks sort of like that, I'm going to draw it a little better. It's a mirror image, yes. That's not very good. Okay, let's do this. Okay, because it's real, it's going to be some mirror image. Okay, so, but that means that you're not going to be okay with overlapping these things. Okay, so any ideas though what frequency we can use? What? Okay, BW, might as well try it. Okay, so let's try bandwidth. Okay, so let's see what happens. That means that the delta function in frequency, that means these things occur at 0 and at FBW and multiples of it, right? Oh no, sorry. We could try this. Okay, let's see. 2FBW minus FBW. Okay, and we're going to convolve, right? We're going to convolve these two things. And what we would get if we did that was, we would get, well, we'd get our original thing, like this. And we'd get another copy of this whole thing shifted over by FBW. There's 0, there's minus FBW, so forth. But we have to keep making copies, so that means we do another copy here. But the problem is, now when we make this next copy, we get this. Okay, so we're going to end up with some aliasing here. Okay, let's do something else though. We can still, there's still quite a bit of room under 4 bandwidth. Why don't we try, yeah? Okay, and then how would you get it back?
Well, you know what you know what you did before the CPs, low pass filter, the basically now. Low pass filter that, and then you make it
Okay, very good. So you're saying, hey, eliminate this to begin with. Only worry about not getting aliasing with this part. When you're done, recover this, and then make a, since you know conjugate symmetry, this was just redundant anyway. You have a homework problem that's exactly related to that in the problem set. It's, and keep that in mind, exactly what was just said on how to do it. There's one funny thing about doing this. You could have done that. Imagine you did that technique. The homework problem just says, forget about that weird spectrum that I gave you. Just take the normal case where you've got a low frequency content. But realize that if it's real, the picture I drew doesn't make sense. It has to be symmetric. Okay? So just filter out this side. And now you can get away with a lower potential. I mean, you have to figure out what's the lowest sample rate you can get away with. But there's a catch to doing this. You might say, well, why not actually do that? And why get away with it? There's a catch, which makes it not actually going to be any more beneficial, but you can think about that for the problem set. So, okay. I mean, it could be beneficial in certain cases, but it's not just going to directly get you, you know, what you're hoping for, like half of the rate or something, sample rate. Okay, but without doing that here, let's just talk about sampling the signal just by itself. Okay, as a real signal. Okay, so let's try this. 2F bandwidth, which would have been, okay, yeah, 2F bandwidth. All right, so now what we have is convolving with something like the following. We have these things now 2F. See, I have a minus here I shouldn't have. Okay. And so what that means is when we do this convolution, we're going to get, I want to keep that picture there, the result is going to be our original copy. And then the next shift of this copy is going to go up by 2 times the bandwidth. So it's going to leave little gaps. It's not right next to the original one. It's got a little gap here. Whoops, no, that doesn't start at 0. It starts right here. That's the next copy. Okay. Now where's the next copy going to be? It's going to be another over here. And like that. And we have to shift both ways. So let's do the copy at, for this delta function here, the negative 2f bandwidth. That's going to shift this one over here and shift this one over here. Now, good news, there's no aliasing going on. Everything's still, there's no overlap. So we should be able to recover things. Okay, so how do we recover? How do we recover x of t from the sampled version? What was that? We that's how we sampled. We multiplied by the delta functions. So recover, we want to filter. Band pass, exactly. We're not going to do a low pass filter. Yeah, if we did the low pass filter as if we had sampled in the normal case, we would be getting back something different than we started with. That's not what we want. So we actually do a band pass filter. Okay. So this is fun, and it actually, at least, what was that? We call it one bandpass filter because any real system is going to be symmetric like that. Yeah. Okay. Notice now that this is satisfying because the frequency content has the same range. Originally we said if the range was from 0 frequency to f bandwidth, then sampling at this Nyquist rate of 2f bandwidth is enough. Now we're saying, well, that's not our content, but we have the same range of content. We're just at higher frequencies. Turns out we don't need to sample at any higher of a rate. This isn't generally true. You couldn't shift this bandwidth anywhere you want. Because if you try it out and do the sampling, you'll see you'll get aliasing. This was sort of a special case where we were at a multiple of the bandwidth, and that way things did not overlap. Okay. So this is another intuition for why discrete time signals. What's the property that we know about the discrete time Fourier transform? What's the first property that comes to mind? Periodic. Okay, discrete time Fourier transform is periodic. And now we see that once you've sampled any signal, you always end up with a periodic Fourier transform. So that matches up. Another intuition for why the discrete time Fourier transform is periodic. All right. One thing to note is that if you've played around with the settings of a DVD player and software or something, you often have these anti-aliasing filters that could be used to make video look better or images. And the reason is because digital images are represented with pixels, which means they're sampled, right? And because they're sampled, you can get aliasing. If you have something that's high frequency, say a screen door, that's very high frequency and the resolution of your image is not high enough, then it can give you a weird low frequency artifact that is aliasing. Doesn't look nice. And to avoid that, when you go down to a low resolution from a high resolution, maybe you start with extremely high resolution film and you go down to some TV resolution, you need to do anti-aliasing filtering first before going down to the lower resolution. Just like we do an anti-aliasing filter to get rid of the content that's going to cause aliasing in this discussion here. Okay, this is actually particularly important for computer-generated images, because a computer-generated graphic theoretically has infinite precision. You have some polynomial that's describing the edges of your surface, and so the precision is not discrete; it's very precise, which amounts to very high frequency content. So very sharp signals, sharp images include high frequency content. Now, when you go and display that digitally on a digital TV, you're going to cause aliasing if you don't apply some anti-aliasing filter before doing the sampling. Okay. All right, so let's now look at the reconstruction. What's the reconstruction actually doing? Okay, so what you have here is some discrete time signal. And you're going to then reproduce the continuous time signal. And we said the way we do that is a low-pass filter. But conceptually, what we actually had to do was convert this to the continuous time equivalent of that signal with delta functions, where this was zero, that was sampling period, 2 times the sampling period, 3 times the sampling period. And if we look, and then we low-pass filter. Now, low-pass filter was, in time, what is a low-pass filter? It's a sink. And we said that we were using a low-pass filter with cutoff frequency T. So we were using rect of f over, and it was, we wanted the width to be, we wanted it to go up rather than a half. Rect goes out to a half. We want it to go to fs over 2. So we need to spread this out by a factor of fs, right? And we also wanted to have this thing here, 1 over fs, because that was needed to cancel out the scaling that was done during sampling. So if we look back at this reconstruction filter, we want the height to be ts, which is 1 over fs. We want the width to go up to fs over 2. I put negative in one place. Okay, so this is what we want in frequency. We want h of f to equal that. Therefore, h of t equals, and with the scaling property, we have exactly that it is sinc of fst. Okay, now this works out very nicely, because look at what happens with sinc of fst. It means that at 0, so sinc looks like this. It has a height of 1. and it crosses 0 at every TS, at 1 over Fs, and every multiple of that. So forth. So when we do this convolution, we get something very nice. The result of this convolution, the result of this is the following. Let me draw it right underneath this signal over here. We take the sinc. This is the train of delta functions, so we can do each delta function separately by linearity. So we just take a sinc over here. Let me draw a dotted line or a gray line, the original discrete time signal. And what we do now is we take, we end up with a sinc like this, crosses 0 at every other sample point. Okay, so that is the contribution of convolution. The convolution then will be the sum of the convolution of each of these deltas. So we're going to have a sum of these separate signals here. Do this. Okay, and last one here. Okay, so we see a couple of things to notice. One of them is that it's very easy to verify that this reconstruction at least matches the sample point. Okay, so we're claiming that this reconstruction actually matches the entire X that we sample. But it's easy to check it at least matches the sample point, right? Because when you add all these sincs together, all of them are 0 except the one that was convolved by that delta function. Okay. So and the other thing to notice is that to calculate the value of this reconstruction at any one point, it actually depends on every other sample infinitely far away because the sinc never ends, right? So the reconstructed value in between sample points is influenced to some degree by any sample as far forward or backward in time as you want to look. That's a bad thing in terms of in implementation. Of course, we're not really going to be implementing a perfect low-pass filter, but that's okay. For now, let's just assume we can implement an almost perfect low-pass filter. It doesn't have that property. But for ideally, if you wanted to go through and say, let me calculate by hand the value of x of t at some point, you have to sum up an infinite number of contributions. Unless, of course, all the samples are 0. All right, then you know the contribution. Okay. Okay, great. Now you realize that we can also do something, what you might end up finding yourself doing if you play around with signal processing, or maybe for labs in this class, is actually taking a discrete time signal and changing the sample rate. Maybe you have a CD audio signal that's sampled at 44 kilohertz, and maybe you don't want so many samples. You only care about looking at low frequency content or something. So you want to do what's called downsampling. All right. Well, that means that you have some discrete time samples, and you want to end up with, you want to get, say, every other, let's say, factor of 2 downsampling. You want to go ahead and get, you only want samples at every other time. You don't want to have so many samples, such a high sample rate. Maybe the processing is difficult. You're trying to do something in real time. Then how do you appropriately do this? So you would have a discrete time signal. We only ever look at the Fourier transform from -½ to ½ because it's periodic. So there's XF, something like this. And you've decided that you know that by downsampling, you're not going to be able to represent the entire spectrum here. So you decide that you're willing to live with only half of the spectrum because you're going to downsample by a factor of 2. So then you can low-pass filter this. Okay, so low-pass filter before downsampling. To avoid aliasing. Now you can do the same derivation we did in continuous time, which is to say that a downsampling is like what we call a decimation, where we zero out all the in-between stuff and only take. So this type of, this here, let me say decimation, is not what we would ideally want in downsampling. We don't just want to throw away every other sample without first applying a low-pass filter. So this, just throwing away every other sample, for factor of 2 decimation, is, we call that decimation, and we could analyze what that will do to the frequency content the same way we did in continuous time. This is multiplication with a train of delta functions. And under the same, for the same reason, if that's going to cause copies of this, and it's going to lead to aliasing if we don't first filter it. So we low-pass filter, and in general, we low-pass filter with a cutoff frequency 1 over 2k, where k is the ratio of downsampling. Okay. If you use the command resample in MATLAB, they automatically do the low-pass filter for you. So they don't just go in and throw away every other sample. They first do low-pass filter to avoid aliasing, and then they decimate. And they compact it. Similarly, you can upsample. Upsample, and this is like reconstructing the continuous time signal. So now we're trying to recover the parts that we're missing. So we have some signal here, and we basically want to fill in. We want to go to a higher sample rate for some reason. Okay, so now we want to fill in missing points. So we first spread our signal. fill in missing points by spreading it, which is this operation we've talked about several times. So what we have now is this, 0 in between. This is what we were calling, if this was xn, then this here is xkn, or in this case 2 of n. We've used this several times in problem sets and so forth. So we just spread it in time. Okay. And then what do we do for our final step? Any guess how we fill in the missing values? We low-pass filter. Okay, so this is a lot like reconstructing the continuous time signal from the samples. We're reconstructing a higher sampling frequency from a lower sampling frequency. So here what we do is so we had these points like this, and we do low-pass filter, which is equivalent to sync interpolation at the right frequency. That's like, oops, like this. Of course, we only are calculating, we're doing a discrete time low-pass filter, so we're just calculating these missing values here. So we only need to calculate the values at the in-between points, which will be something like this, this, this. So our result is now an upsampled discrete time signal, twice as many samples. And we filled in the missing ones using a low-pass filter. Yes?
How does the Fourier transform look like when you Fourier transform?
Okay, great. Good. So we, okay, so here's a Fourier transform here. F goes to a half minus a half. It's actually a great exercise to go mathematically and plug this x sub k of n into the discrete time Fourier transform and verify what I'm about to show you, which is that if we started with a spectrum like this, and then we look at, so that was x of f, and this is x2 of f, upsampled with a factor of 2, it actually looks like this. So you see that we've shrunk everything, just like in continuous time. If we spread the signal in time, we condense it in frequency. We've done the exact same thing. You have that same property in discrete time. In fact, maybe this was in your problem set, where I asked what happens, what's the property of, what happens to this under the Fourier transform. I think that was in one of the problem sets, either 2 or 3. And the answer is it shrinks just like it does in continuous time. But remember, because it's periodic, when you compress in frequency, you have to bring those extra periods in. Okay? So you get something weird like that. And if you, then what we're doing is we're doing a low-pass filter just to get this part of it. So then the last step here, after upsampling, looks like this. 1/4 minus 1/4. After low-pass filter. All right? Okay, I want to do something here related to filtering. Okay, because I need to cover something that's related to one of your problems in the problem set. Yep?
For step 1, why can't you just take a low-pass filter of that with appropriate frequencies?
You mean a low-pass filter of this?
Yeah, like why do you have to double it? Because aren't them like, okay, you spread them out, then you take the low-pass filter, but then don't you have to like squeeze them back in? Like aren't they at different points in time now? Like
they are, but the whole point was we wanted to go from a lower sample rate to a higher sample rate. So when you have a higher sample rate, like let's say you took a CD audio signal of 44 kilohertz, and then you said, oh, I only want to look at the lower portions of the spectrum, and I want to do some processing. I don't want to have such a high sample rate. So you do some appropriate downsampling to have a sample rate of 10 kilohertz, let's say. Which, in order to get there, you had to be willing to throw away the high frequency content of your signal when you did the original downsample. Now you're done with whatever processing you want, and now you want to take it back to a CD format with 44 kilohertz sample rate. Okay. Well, you're going to end up with more samples. That's the whole idea. When you go down in sample rate or up in sample rate, you're either throwing away a bunch of samples and ending up with a shorter signal, in a digital signal, or you're adding them back in, right? And this is the adding them back in. So you are going to end up with it spread out. But we're just trying to figure out how do you end up not with this sort of weird behavior where you've got zeros every time. The frequency here will help you understand that there's not really a way to low-pass filter before you spread it. Once you spread it, then it makes sense to do a low-pass filter to get rid of these. But before you've done not decimation, but the spreading here, there isn't really a filter you'd want to apply. Okay. Yeah. Mm-hmm. Yes. It will not look like this because you had to get rid of this part of it. You're right. So if this is how you started, I didn't necessarily mean for these two to be the same signal. I just used the same drawing. Because if you started with your high frequency content looking like that and you did a downsampling, the result would just look like this inner part spread out, right? It wouldn't look like this picture. Yeah, I should have. That's a good idea. Draw this one to match the other one. All right. Okay. Let's look at how filtering, which we talked about last week, but we want to talk about how. What is the significance of phase? Okay, because it's often a habit, first of all, of representing magnitude and phase in separate plots. And in fact, sometimes you'll catch yourself only caring about this magnitude part. So what's the significance of the phase? So the phase, we know if it's a real system, it's going to be conjugate symmetric, so the phase is odd. Okay. Now, there is a nice interpretation of phase. For one thing, phase of a signal captures all the timing information of that signal. Okay. Now, there's a very nice demo that I didn't prepare, but I'll explain, and you can find it online or even try it yourself. And that is take two images of the same size and take their Fourier transforms and take the magnitude of one and the phase of the other. Okay, so make one Fourier transform out of these two that has the magnitude of image 1 and the phase of image 2. Now take the inverse Fourier transform and take a look at it. What will it look like? I'll tell you, it's not going to look like a morph of the two. It actually looks more like image 2, the one you took the phase from, than it does like image 1. I mean, it won't even look at all like the one from image 1, but it'll look very much like image 2, the one where you kept the phase. Because, and the reason is because a lot of images, the rough amplitude is quite similar, but the phase captures all of the timing information, the location of where things are in the picture. If you throw out the phase, you pile all of the energy off at the origin, and it doesn't look at all like the image you were interested in. Okay, so what we have here in filters, we can understand phase by starting with something called a zero phase filter. Okay, suppose in time that h of t is even. So we have some filter, for example, sync. I'll just draw something else so we don't always talk about sync. So you have an even impulse response. Okay. Now, it's not causal. If it's an even impulse response, it's not going to be a causal system, but don't worry about that. What do we know about the Fourier transform of this even, and it's real. We'll assume real in many cases. So you have some even and real h of t. Then what do we know about h of f? It's even and real. Okay. H of f is even, and more importantly here, real, which means the phase of h of f equals 0. Okay, for all f. Now technically it could be 0 or pi, and because if h of f is negative, we often say you keep the amplitude positive and you say that the phase is pi. But we'll consider that all 0 phase. There's a reason we're doing that. There's a technique called phase unwrapping that keeps the phase continuous. And if you do phase unwrapping, then you'll get that this always will have 0 phase. Okay. So that's what. So a 0 phase filter is a symmetric filter. Has to be symmetric. Now, what if we have a symmetric filter if h of t is symmetric about capital T? All right. Now we can understand the phase, because that means that h of t plus capital T, all right, is even. Okay, and that means that h of f times e to the I 2 pi tf is real. 0 phase. Therefore, the phase of h of f equals negative I 2 pi tf. Okay. All I did here was that this phase is 0. What is this phase? This phase is the phase of f plus this exponent. Okay, phases add when you multiply two complex numbers. So because phases add, the sum of this plus this equals 0. Therefore, this is negative. Okay. Yeah. Plus t, because I started symmetric about t, and I need to shift it back to 0 to make it even. So I need to shift the other way. Okay, so this is linear phase. So linear phase filter, if If the filter has linear phase, it's a shift. It's symmetric about some point. Now, this is important because sometimes people design filters to be linear phase on purpose. If you remember the windowing method that I mentioned in class about designing a filter, you start with an ideal low-pass filter or whatever filter you want. You window it by cutting off the edges, and then you delay it to make it causal. Okay? If you do this, and if your ideal filter was zero phase, which it often is. I mean, often people are designing ideal filters just by their amplitude, and they leave the phase zero. What that means is that when you window it, you're going to get an even function, and then when you delay it to make it causal, you're going to have an H of t that's symmetric about some point. Okay, and the phase of this system is known to be linear phase. Now, why is linear phase interesting? Well, here's why. Because now I'm going to just tell you something called group delay. Group delay says that if you have a frequency that's if you have some frequency content that's localized in time, so let me say you have something like this, and this frequency is f, and you say, what's going to happen when I pass this through my filter? Okay, this isn't just a pure frequency, but if you look at the Fourier transform of this, it's going to be concentrated around f. And when I pass this through my filter, what happens is I end up with a scaled version of this thing, often delayed by some amount. Okay, let me draw it scaled. So maybe it was, cut down a little bit here. And this delay here we call the group delay. Group delay. It's basically saying if you have a narrowband signal, how much does it get delayed as it passes through your filter? And you have this remarkable property, and that is that the group delay is a function of f. Group delay of f equals 1 over 2 pi times the derivative of the phase of f with respect to f. Okay, and I will, because we're out of time, I will justify this next time, but I have a demo. So let me demo it here. Okay, so here's the demo I came up with. Okay, here is a filter. I created a filter. You don't have to worry about what the impulse response is of my filter. Here is the frequency response and the phase of my filter. Okay, this is hertz here. And I want to point out that the filter, for one thing, it passes through, that's on the log scale. So it passes through frequencies at about 5 hertz and frequencies at 10 hertz. Between that, even though it doesn't look very far down, on a log scale that's significant, so it basically cuts out frequencies that are not near 5 or 10 hertz. So let's look at the phase. The phase, around 5 hertz, I have one slope. And I'm saying the group delay depends on the slope of the phase. So I have one slope here, and around 10 hertz, I have a much steeper slope. If we calculate if we go through and calculate this slope, well, qualitatively you can see that this is a larger group delay than this one. Okay, so now I have a signal here. This signal looks really ugly, but it's actually the sum of 3 frequencies. Okay, and the 3 frequencies are 5 hertz, 7 hertz, and 10 hertz. Okay, and notice that I've also kind of localized them in time by multiplying them by this Gaussian kernel, this e to the negative x squared. Okay, just to make them localized in time. Now I'm going to pass it through the filter, and what's going to come out is, it should come out that the 5 hertz one is delayed a little bit, the 10 hertz one should be delayed a lot, and the 7 hertz one should be basically eliminated because of the amplitude. Okay, so let me remove this comment here. Okay, so this is what comes out. All right, so it's like we said, the low frequency one is barely delayed here, right? And the Now, notice the amplitudes are different. I didn't keep the vertical scale the same. This should be smaller. Okay. But the high frequency one comes out later. And the in-between frequency is basically eliminated because it was filtered out. Okay, so this is a demo of group delay. This went in, and this came out because of the group delay. We'll kind of derive group delay next time.